Okay, it has been a great honor to speak in this very special occasion and to this very distinguished group about our recent work on the multiple analysis ensemble. Multiple analysis ensemble initialization of ocean on seasonal prediction and of ANSO and Asian monsoon. And the first, I would like to thank Professor Shukla for his support and guidance in our work. And I would also like to thank many scientists in COLA, especially Dr. Jieshun Zhu and Chaosu Shen, and also many colleagues in this community outside and inside COLA for their contributions. And first, I would like to, as a former student of Dr. Shukla, and I would like to take this occasion to thank Dr. Shukla for his guidance and for his encouragement, and in so many years to even now I always think Dr. Shukla as my advisor. So when I have anything I feel excited, I think the first person I would like to talk to is the result to talk to is to Dr. Shukla, and I think this is a quote I get about the highest level of teachers. The great teacher inspires, and Dr. Shukla is really inspiration to me. So thank you very much, Dr. Shukla. And in preparing this presentation, I also noticed that in my work, starting from the dissertation work, the upper ocean heat content has been a theme to work on as a source of predictability. And this is one of, I think, a continuation of my dissertation work. And in this, we have found a pattern of upper ocean thermocline anomalies, which we think has been responsible for the low frequency variability in the tropical Atlantic Ocean. And we think this is probably a source of predictability in the Atlantic Ocean. Also, even today, I think the dominant view is Atlantic Ocean is dominated by the surface wind evaporation SST feedback. But we think probably someday we can verify that this kind of subsurface anomalies also have a role to play. And this is another paper we have worked together. This shows that have studied the Indian Ocean, tropical Indian Ocean, upper ocean heat content change. This is from the, I would say, a COLA version of data simulation. And this is a simulation using the COLA model for demonstrate that forced by SST outside the Atlantic Ocean, we can recover a lot of this kind of low frequency thermocline change. So this is also a source of the Indian Ocean variability in this region. And so now we already come to the stage that ocean initialization becomes a very important part of the climate forecast, from intra-seasonal to seasonal to interannual variability. So so in that case, the initial condition, the accuracy of the initial condition becomes a very important issue. So this is a demonstration of how well we have been doing in the upper ocean heat content. This is 300-meter ocean temperature, average ocean temperature from 6 state-of-the-art ocean reanalysis system. And this shows the signal-to-noise ratio. And the signal basically is the ensemble average of these 6 products. And the noise basically we define as the deviation among this group. And you can see that in the tropical Pacific region, the signal-to-noise ratio actually is quite high, probably thanks to the Togotau array in this area. In the Indian Ocean, there is also reasonably high in the three tropical oceans. So you can see that the center of actions we have demonstrated in the last figure has shown here actually has a high signal-to-noise ratio region. But when we come to the tropical Atlantic region, the signal-to-noise ratio actually is noticeably lower. So in that region, if you do a ULF analysis of each of the products, you will find that even their leading mode shows qualitative differences. So it's not really very similar to each other. But the situation probably not as bad as we at first looked. If you do an ensemble multi-analysis ensemble average, you will find that their leading ULF mode, actually you project each of the analysis onto this is the first two ULFs, you will find that the signal-to-noise ratio is much higher than before. And also, then you look at each of them, then the spread we have shown before. And also, these patterns are actually clearly shows some very consistent physical pattern. For example, this is basically the lower frequency, the thermocline change we have seen before. And this is actually the very clearly shows the so-called Atlantic Nino pattern in the Atlantic Ocean. So from this, we can say that the signal actually exists in all of these analyses. But there is the ocean analysis, on the other hand, still have a lot of noise in it. So a lot of unrelated, so the current data probably not very highly can control the system totally. So there is still noise in each of these systems. So the question is, this is the worst, probably the worst scenario in our analysis. If we look at the best part, so this is the Pacific Ocean. Actually, the signal-to-noise ratio is very high in the two leading modes. And this two mode is very familiar to us and crucial for the ENSO cycle. But if you look at their qualitatively, for example, for a certain segment, you will find that different analysis actually shows a kind of a range of variability. Also, there is apparently a lag from one of the analysis to another. This is actually if you do a seasonal forecast or even an intra-seasonal forecast, this is probably will cause a difference. So our question is, there are two interrelated questions. First, what are the effects of uncertainty in the upper ocean heat content on ISI prediction? Second, will ensemble initialization, we propose to use the ensemble initialization of use different ocean from different ocean analysis can improve this ISI prediction. Okay, and we have for this to demonstrate this, we have conducted a set of handcast experiment. We use the NSAP CFS version 2 as our forecast system. So it's also we conduct two sets of handcast experiment. First, we call it MAE, so multiple analysis ensemble ENSO onset handcast experiment. This is a 1-year experiment and initialized by 4 different ocean analysis. So which one actually doesn't matter very much. And we have made a forecast for 1 year from April, probably because that's generally the time the ENSO start. And also we also for each of the analysis, we have also used the perturbed atmosphere initial condition. The second set we conducted later and just finished recently is so-called monsoon analysis. We basically use the same strategy, but first this one we use anomaly initialization, but this one we use full initialization. Also, this is a target on monsoon, so we start with the initial condition from January to May, but end all the handcast in September, end of the monsoon season. So I will show some quickly show some results from this handcast. This shows the SST prediction scale, correlation scale from the first set of handcast with lead mounts 2, 5, and 8. You can see that, and this is the 4 different ocean initial conditions. And this is we call it probably we can call it MAE ensemble, MAE mean ensemble. So you can see that even from month 2, there is already have a scale difference. And by the end of this, close to the end of this forecast, you can see there is clearly different scales. Some are better, some are somewhat worse than the others. But the ensemble average is always, I think, is in all these cases are close to the best. And this can be also seen from this. The first two basically give the same information. You use the Nino 3.4 index as our target, and you can see that the ensemble mean, the total ensemble mean, is always close to the best for each of the ocean analysis. Also, there is a quite large spread from different analysis. Use both correlation and the RMSE measure. And another probably useful information is that the spread and the RMSE ratio, which is actually a measure of the reliability. In the ideal case, it should be close to 1. And if we use the ensemble, like a total ensemble average, you will find that it actually increased. So it basically shows that the forecast becomes more reliable. So in this case, in this case, we can see that the first one is generally better. So this is from one of the ECMWF ocean analysis. But it's not always like that. So for example, this is our more recent handcast scale of the Nino 3.4. From different lead months, like I started with January, February, March, and to May initial condition. If you look at it carefully, you will find that there is no one like ocean analysis consistently from all initial conditions produce better forecast. But on the other hand, the ensemble average, total multi-ocean analysis ensemble average is always among the best. So this shows that this method is really a useful method of generating ocean ensembles. I think currently most of the ensembles are generated from perturbation in the atmosphere, but there is not a very efficient way for ocean ensembles. Okay. So I think I will quickly go through our more recent analysis. So we also find this is not confined into the ENSO. For example, Indian Ocean, this is we have shown as a critical region, also have very strong, also shows stronger, higher scale in the SST. And this partly can be, our more recent analysis also shows that whether it can affect the precipitation, for example, in the monsoon region. And our preliminary analysis first shows that in the monsoon region, a very interesting phenomenon is that the forecast scale is not very sensitive to the initial conditions. Actually, long lead forecast is very close to the short lead forecast. This is because actually Asian monsoon have two modes. One is actually with contemporary, forced by the contemporary ENSO. One is forced by the like a delayed ENSO effect from previous summer or previous winter SST anomalies. Actually, the second one is much longer lead than the first one. And the example actually shows that this is 1997 to 1998 forecast. This is from the observation. This is from our handcast. And you can see that in 1997, the contemporary actually is not that successful because the model didn't anticipate the strong Indian Ocean dipole. But in the 1998, you can see the pattern is very well predicted. And this is actually true for all the strong ENSO we have analyzed. And so as a quick summary for this, actually, I don't have time to analyze its reason. Basically, it's the delayed effect in the Indian Ocean SST and in the Western Pacific region. Okay. So for this, in summary, we can say that there is a considerable amount of uncertainty exists in the upper ocean heat content of current ocean analysis. And ocean uncertainty actually causes a noticeable spread in ENSO prediction. This is the best case. In other regions, it should be even larger. But the multiple analysis ensemble initialization should have some improvement in certain regions. And also, this improvement in SST can affect the other variables, such as the precipitation forecast. And finally, our preliminary result, this is probably not strongly related to the multiple ensemble, but an interesting fact is that the ENSO, so following ENSO event, Asian monsoon, summer monsoon is more predictable because of the delayed ENSO effect. Thank you.
Hi, can you comment a little bit about use of salinity observations and affecting the density field and whether you think that's going to help?
This part we just use the salinity. Actually, we just use the analysis we have. Actually, Jie Shun has done another set of experiment which like to replace the salinity with its climatology and compare with the real-time salinity. We do find several very interesting cases. The salinity have played a very dominant effect. I think at least one case for a cold event in the past 20 years. This paper has been published in scientific report, I think in Nature Scientific Report. So salinity actually initialization is an important factor in certain cases.
It also relates to the use of sea level observations.
Right, exactly, yes.